Aerodynamic forces on road vehicles. Dynamics. Automobiles and trucks are now the subject of much research on aerodynamic forces. Both lift and drag, at least, are important in vehicles' aerodynamics. At least one textbook is devoted to this subject. There is various references. A very readable description of race car drag is given by Katz, consumer manufacturer, right? And government interest. Has cycled between high speed, high horsepower and lower speed drag. Let me write to high speed, high horsepower, and lower speed, lower drag. Better streamlining of car shapes has resulted over the year in a large decrease in the automobile drag coefficient, as shown in the provided picture, which shown here. Modern cars have an average drag coefficient of 2500, these type of cars. Based on the frontal area, since the frontal area has also decreased sharply, the actual new raw drag force on cars has dropped even more than indicated in this picture. The theoretical minimum shown in the figure is 1500, is about right for a commercial automobile, but lower values are possible for experimental vehicles. Note that basing drag coefficient on the frontal areas is awkward, since one would need an accurate drawing of the automobile to estimate its frontal area. For this reason, some technical articles simply report the raw drag in newtons or pound force, or the product of this relation. Many companies and laboratories have automotive wind tunnel, some full scale, with moving floors to approximate actual kinematic similarity. The blunt shapes of most automobiles, together with their proximity to the ground, cause a wide variety of flow and geometric effects. Simple change in part of the shape can have a large influence on the aerodynamic force. The another figure that shows here illustrates force data. The force data collected by Bierman For an idealized smooth automobile shape with the upsweep in the rear of the bottom section. We see that by simply adding on the upsweep angle of 25 point, we can quadruple the downward force, gaining tire traction at the expense of doubling the drag. This point. For this study, the effect of a moving floor was small, and a 10% increase in both drag and lift compared to fixed floor. It is difficult to quantify the exact effect of geometric change on the automotive forces. See, for example, changing the windshield shape may interact with downstream flow over the roof of a tank as shown in this picture. Who found and tried. Nevertheless, based on the correlation of many model and full-scale tests, there are references a formula for automobile drag that adds separate effects such as front ends, curves, fenders, windshield roof, and rear ends. This figure shows the horsepower required to drive a typical tractor-trailer truck at a speed of 18 miles per hour. The rolling resistance increased linearly and the air drag quadratically with speed as c equals to 1. This is an example of the drag coefficient on the vehicles. Progress in computational flow dynamics means that complicated vehicle flow field can be predicted fairly well. So due to this experiment, there are various methods to drag reduction. Sometimes drag is good, for example when using a parachute. Do not jump out of the airplane holding a flat plate parallel to your motion. Mostly though, drag is bad and should be reduced. The classical method of the drag reduction is streamlining. The classical method of drag reduction is streamlining. For example, nose fairing and body panels have produced motorcycles that can travel over more recent research has uncovered other methods that hold great promise, especially for turbulent flow. More recent research has uncovered other methods that hold great promise, especially for turbulent flows. We can categorize the methods for the drag reduction as application of oil pipelines. Introduce an annular strip of water to reduce the pumping power. So using of the annual strip. Annular strip to reduce the drag on pipelines. of oil. The low viscosity water rides the wall and reduces friction up to 60%. To friction, we have a reduced friction, 60% friction. Turbulent friction in liquid flows is reduced up to 60%. By discovering a small amount of high molecular weight polymer additive, turbulent friction in liquid decreased 60% with high molecular weight polymer additive. High molecular weight polymer additive a stream-oriented surface with a stream oriented surface V groove micro oriblets. Micro-oriblets. Without changing can reduce turbulent friction up to 8%. Paragraph 4. Small near-wall large eddy break-up device. Small near-wall large eddy break-up device. Device LEBU reduce local turbulence friction up to 10%. Turbulent friction up to 10%. Air microbubbles injected at the wall of water flow create a low shear bubble blanket. At high void fraction, drag reduction can be 80%. Air microbubbles injected to the wall of water. Six, span-wise wall oscillation. may reduce turbulent friction up to 80% and 30% decrease, and the active flow control also active control also, especially of turbulent flow, is the wave of the future. As reviewed in various references, this method generally requires expenditure of energy but can be worth it. For example, tangential blowing at the rear of an auto evokes the Honda effect, is which the separated near wave flow attaches itself to the body surface and reduces auto drag up to 10%. Drag reduction is presently an area of intense and fruitful research and applies to many types of airflows and water flows for the boat, vehicle, and conducts. The next description is drag of surface ships.